Okay, so continuation video. So from the previous video, we have already solved for the allowable stress and the design stress of this cross-sectional yield limit state and the tensile rupture stress limit state. So the next thing that we should solve for is the block shear. So it is also said here that we must solve for the nominal block shear strength of this tension member right here. Okay, so though it is indicated here that we must solve for the nominal block shear strength of the tension member, in designing or in analyzing, you must solve for the block shear strength of this gusset plate right here and the tension member itself. But coincidentally, if you can see here in this, in the given, it is said here that they have the same thickness. So 3/8 inches, 3/8 inches, and they both are in a 242 grade 50 specification. So meaning that whatever you would be solving for this member right here would also be the strength of this gusset plate right here. But if not, so let's say that the properties of this gusset plate right here is different from the properties of this plate right here or this tensile plate right here. You should solve for their individual block shear strength and choose the smaller values. So that's if you are required to solve for the block shear strength of this connection right here. But once again, it is said here in the problem that we are only to solve for the block shear strength of the tension member. So it would just be this one right here. If you are to solve for the block shear strength, we would be using this formula right here, which is Rn is equal to 0.6 FUANV plus UBS FUANT, and that should be less than or equal to 0.6 FYAGV plus UBS FUANT. But for pretend that this is to be the smaller value here, this is to be your value for Rn. So basically, the smaller value in between these two equations right here is to be your Rn. Okay, so let's solve for Rn. So what do we need? So for Fu, we actually have that already. So from this, our Fu is equal to 483 and our Fy is equal to 345. So listing them here, Fy is equal to 345 and our Fu is equal to 483, both in megapascals. So MPa and MPa. Okay, so what's next? So we already have our value for Fu. So let's just solve for the value for A and V. So for your A and V, so that is to be your net shear area of, well, your failure. So your failure can either be this one right here. This can be your failure plane, or it can be this one right here. But by experience, as I can see, this is to be the governing failure. Since, as you can see here, 44.45 plus 44.45 is a lot greater than 50.8. So meaning this one right here would give you the lesser value between the two options. So there. If you are not sure whether this is to be the governing block shear setup or the other one, it is better for you to solve for them individually, then compare. So once again, I would be solving for this one right here. So this is to be my block shear failure. So for your A and V, this is to be once again your net shear area. So for your shear area, it would be this one right here. So this one right here and this one right here, whichever is parallel to your force. So once again, this is to be your force. So this is to be your force P. I mean force Rn, I should say. So Rn, this one right here. Okay, so for A and V, it would be this one right here, 38.1 plus 76.2 plus 76.2 minus the diameter of your holes. So from that, I will just be writing it here. So 38.1 plus 76.2 plus 76.2. So that is to be this whole dimension right here up to this center right here, I should say. So this is to be 76.2. Then after which we would be subtracting the whole dimensions right here. So from the previous one right here, the effective diameter of the hole is to be 23 mm. So the hole is equal to 23 mm. So we would be subtracting 23 mm times, so how many holes are there in this setup right here? So that is to be 1, 2, and 1/2 of this one right here. So 1 plus 1 plus 1/2, that is to be 2.5. So if I am to copy this one right here to the next slide, oops, I'm sorry. Your fill area is to be, your block shear area is to be this one right here. This one, and there. So it would be this one right here, here, and just 1/2 of this. So this is to be the one that you would be subtracting. That's why it is 2.5 and not 3. So that is your A and V. But take note, guys, that we have two shear areas. So this shear area right here is identical to this one right here. So I would just be multiplying this by 2. For your net shear area, you must multiply this dimension right here by your thickness 9.525. So 9.525. So our answer here, so our A and V is now equal to, so using the calculator to your left, so that is equal to 38.1 plus 76.2 plus 76.2 minus 23 times 2.5, so closing parenthesis, times 2, then times the thickness of 9.525. So this is to be our net shear area. And from that, our answer here would be 2533. So 2533.65, so millimeter squared. So there, you already have our A and V. So next up, let's solve for A and T. So A and T, so what would be the value for A and T? It would be this one right here. So that is equal to, so 50.8 minus, how many bolts will be subtract? So it would be 1/2 of this and 1/2 of this. So it would be this one right here. 1/2 of this bolt right here minus 1/2 of this bolt right here, since the dimension of 50.8 is to be in this location right here. So this is to be 50.8. And we only need this dimension right here. So that is minus, so half of this, that is 1 times the diameter of the hole, which is 23. So that is for this length right here, and for us to get the area, we must multiply it by the thickness of 9.525. So solving for this, our answer here would now be equal to 264.795. So 264.795 millimeter squared. So this is for A and T. So what else do we need? So it is said here that we also need our AGV. So for our AGV, that is pretty basic. It would be the area of this hole right here, this hole one right here, not considering the holes. So from that is just basically 38.1 plus 76.2 plus 76.2 times the thickness of our plate, which is 9.525. And since we have two shear areas, so multiply this by 2. So times 2. So 3629.025 millimeter squared. So there. So since we already have everything we need, so let's just solve for Rn. So for Rn, that is to be equal to, so 0.60 times FU, and our FU once again is equal to 483. So 483 times A and V, and our A and V is equal to this one right here. So 2533.65. So plus, so I think it is better for me to move this here so that we would be having more space. So let's redo. So Rn is equal to 0.6 times FU of 483 megapascals times A and V, which is 2533.65 plus UBS, and our UBS in this case right here from this table right here from AISC. So we would be using 1.0 since we are to use gusset plate here. So UBS 1.0. So plus 1.0 times FU of 483 times ANT of 264.795. Then we are to compare it with this value right here. So this one. So let's compare it with, so let's choose another color, let's say white. So let's compare it with 0.6 times FY, and our FY is to be 345, and our AGV is equal to 3629.025 plus 1.0 times 483 times 264.795. So from those, let's compare both values. So for the first equation, that is to be equal to 0.6 times 483 times 2533.65 plus 483 times 264.795. So it would give us an answer of 862,147.755 newtons. So that is for the first equation. And let's check if it is less than or equal to the second equation. So 0.6 times 345 times 3629.025 plus 483 times 264.795. So our answer here would be 879,104.16 newtons. And as you can see here, this is to be our governing value since this is to be less than this one right here. So if I would just be copying this to our summary. So where was our summary a while ago? So here. So since this is to be the governing value for block shear, so block shear. And from the problem, we are only to solve for the nominal block shear strength of the member. So nominal meaning that is to be Rn. But if you are to solve for its allowable strength and its design strength, so its allowable strength would be, so for our Ra, that is to be Rn over omega. So our omega here would be equal to 2. And for our LRFD, our phi is equal to 0.75. So depending on what you are solving. So if you are solving for ASD, use this. If you are solving for LRFD, use this. Okay, and after that, choose the governing value right here, whichever is smallest. So there, but since once again we are only to solve for the nominal block shear strength of the tension member, we are now done with our problem. So there, if there are any questions, feel free to message me.